28-4 is about Ampere's law. Ampere's law is really important because it's one of Maxwell's 4 equations. And Maxwell's 4 equations describe everything there is to know about electromagnetic waves or electromagnetic theory. It looks very, very similar to Gauss's law, which is also one of Maxwell's 4 equations. It says the integral. Notice it's an integral over a closed path of B dot dl is equal to mu 0 times the enclosed current. That reminds me an awful lot of Gauss's law, where it was the integral over a closed surface, and it equaled the electric field times dA. I can even write it. We're going to erase it, but this was Gauss's. It has a very, and this was also an enclosed charge, has a very, very similar look. So the better you understood Gauss's law, probably the easier this is going to be. But instead of an enclosed area, this is actually a closed path. So first thing is the integral must be taken around a closed path. The second part thing I want to mention is, since this is a dot product, the dot product assures that the parallel component of B is taken. So we're only interested in that part of the magnetic field that is parallel to the path, okay? DL is a little segment of the closed path. So we're interested in that part of the magnetic field that's parallel to the closed path. Okay, let's look at an example. I'm going to have to erase all of this so we have room to work. Let's consider a long, straight wire carrying a current I. So here we have it. Here's our long, straight wire, walk straight up. It's got some amount of current I flowing through it. We think about, let's see how to draw this. There we go. I've kind of drawn like there's like that piece of wire is going through a piece of paper or something, because I want to draw, if I draw the magnetic field lines, I know the magnetic field, if I grab that wire, is going to make a circle. It's going to look like this. I'm going to draw a circle for that particular location. So there it is. There's the magnetic field lines. Notice if I make that a circle with a radius of r, that the magnetic field is parallel to the circle at every point, or the magnetic field is parallel to each little segment DL. I could put a little bitty segment right here. That's a DL. Okay. So what's this mean? It means when I do the integral of B dot DL equals mu naught I, since B is parallel to each one of these little segments, this is just going to come out to be B times the circumference of a circle, or B times 2 pi r equals mu naught I. If I solve that for B, I get mu naught I over 2 pi r. That's the exact same formula that I got for the magnetic field of a long straight wire. Okay. That's exactly what we just developed in section 28-1. Ampere's law is sort of like Gauss's law. It really is only going to be helpful when we can use some symmetry, but I'm going to solve at least one more example so you can see how it works. And the one on the homework, I think, is probably really very, very similar to this. This is example 28.6, and they want us to find the magnetic field inside and outside a wire. So here's our wire. Looks like this. We'll let it have a radius of r, and of course we'll let the current look like it's going that way. If we want to look at what happens inside the wire, let's just look at the end of the wire. There's the center, it has a radius of r. If I want to know what is the magnetic field at some other point inside, let's suppose I want to know it at some other value of r. So we're going to draw a circle, not a perfect circle, but a circle right there. So we're looking at what the magnetic field will be if little r is less than r. And little r is this radius I drew right there. So if we remain inside of the wire, okay? Well, the real thing we're going to have to figure out, we know that the closed interval of B dot DL, and again, this is a case where it's really easy because the magnetic field will be parallel to DL at every point. So we'll just get B times 2 pi r. But it equals mu 0 I enclosed. I need to know how much current is enclosed by that blue dotted line. Okay. The full current of the whole circuit would be I. It's really just going to be the ratio of this smaller area to this larger area. So the enclosed current is the ratio of the smaller area, pi r squared, to the larger area, pi capital R squared, times the original current I. That's this current that's flowing through the whole thing. Okay. You can see right away that those pi's will cancel. So it's really just going to be r squared over capital R squared times I. That's our enclosed current. So let's see. So this side is B. When I integrate DL over that, I just get a circle, a circumference of 2 pi r. mu naught, and I just figured out that my enclosed current is R squared over R squared times the original current. I just want to solve that for B. So I have mu 0 R squared I over 2 pi R capital R squared. I have to clean that up a little tiny bit. I can see that one of these factors of R is going to go away because of that. So I end up with B equals mu 0 I R over 2 pi R squared. Now notice in this situation, I is a known constant and R, I was the current, R was the radius. So this is all constant except for this R. So what we find is the magnetic field inside is directly proportional to little r. It directly depends on how far you are from the center. Okay? When you finally reach all the way to big R, if we wanted to go at R, at little r is equal to capital R, we're going to see that this turns into B equals mu naught I over 2 pi capital R. That looks exactly like section of 28.1 again. Okay. Let's do the other part. If we're looking at outside of the wire, I'm going to keep those two. This was inside. R less than R. The second box was at R equal R. So let's look what happens when R is outside of the wire. If I draw a picture now, here's the end of the wire, radius R. But now we're interested in something like this. That's when my little r. So this is part B, or I did it as part B. I think they did A and B, different order in the book, where little r is greater than R. Again, our formula is closed interval of B dot dl equals mu naught I enclosed. Well, if we're outside, the entire current is enclosed. So this, we don't have to do anything fancy. We know that the enclosed current is the current I. Okay? We know that's a constant. We know the magnetic field is parallel to any little dl. If I draw a little segment dl right here, well, the magnetic field is parallel to that right there. So this comes out to be B, 2 pi R, mu naught I. So we're back to that same formula that we expected from before. All right. Notice at this point, now this one, there weren't any variables left. When R is equal to R, we know exactly what that is. If R was less than R, this was directly proportional. This one is 1 over R. This one, B, is inversely proportional. So if I were to draw a graph of how the magnetic field strength varies, whether we're inside or outside, it would look like this. It would be directly proportional anytime R is less than R. So it would go up, 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 directly proportional till we reach that value, which would be this number right here, mu 0 I over 2 pi R. Okay. So anytime, so when we're starting here and we let R go from here to here, it's directly proportional. At the surface at R equal R, that's the strength. And then after that, it's inversely proportional. So that's an example of how we can use Ampere's law to understand what the magnetic field looks like inside of a conducting wire, right at the surface of the conducting wire, or even then again outside of a conducting wire. I'll kind of reorganize this because I want to do one more thing. Here's what we found. That's inside. And then finally, if we let the R is greater than R, okay. So inside the wire, we're only part, this is because at that point, if we're inside, the enclosed current depends on how close we are to the center. This is at the surface, and then if we're greater than that, it looks like this. If we want to put some specifics, this is part C on that question, says, if the radius of the wire was 2 millimeters and the current was 60 amps, let's see if we can find B at 1 millimeter, 2 millimeters, and 3 millimeters. Okay. Well, 1 millimeter, but here's my wire, draw it. If my wire has a radius of 2 millimeters, that's my value for R. So 1 millimeter would be like this. 1 millimeter is finding the magnetic field at a point inside the wire. That's that first formula. On inside the wire, it's mu naught, which is 4 pi times 10 to the negative 7, times the current, times R. 1 millimeter is 1 times 10 to the negative 3, over 2 pi R squared. 2 millimeters, of course, is 2 times 10 to the negative 3, and that was squared. That came out to be about 0.003. Now, we do have 2 significant digits, so I'm going to put an extra 0, Tesla. So at 1 millimeter, we would use this top formula, and that'd be our result. At 2 millimeters, we can just use the second formula. That's for R equals R. So I'll call this, that's at 1 millimeter. At 2 millimeters, it's just mu naught I over 2 pi R. So 4 pi, 10 to the negative 7, current was 60. 2 pi, and of course R was 2 millimeters, or 2 times 10 to the negative 3. If I put that in, that second magnetic field strength came out to be about twice that much, 0.0060 Tesla. Well, that makes sense. If we're twice as far from the center, we contain more current, and we actually double our magnetic field. Okay. Our last one, and I'm going to have to erase this to do it, what happens at 3. If we're at 3 millimeters, we're outside of the wire. At 3 millimeters, or out here. There's our circle. Here's our relationship. That's the same formula from the very beginning, mu naught 4 pi times 10 to the negative 7 times a current of 60 amps, 2 pi, and this time R is 3 millimeters or 3 times 10 to the negative 3 meters. And we would expect as we move further away outside that magnetic field will be going back down. It's inversely proportional. And it came out to be 0.040 Tesla. So it behaved exactly the way I would have expected it to behave. So that's our lesson over Ampere's law. If you really do understand this particular example well, I think you're in good shape. If the enclosed current is 0, then the magnetic field is going to be 0. But we do need to pay attention to symmetry and whether or not it really applies. But I think what we did today will be all you need to understand. So the next one, we're going to talk about some particular types of things, solenoid, well, in particular solenoid, and just a little bit about permanent magnets and ferromagnetic materials.